So this will be another easy day, I think. Transformations, which you should have done a ton of last year. And the first thing that your notes say is to see the handout on algebra's common graphs. I'm not going to give you a handout, but next to that, write page 195, because in the book, there's a pretty nice little note box on what parent graphs I think you should already know, and actually we do know more than just these, and we'll slowly get to more and more, but there's the constant function, which is just y equals a constant number. This is just your linear function, so just y equals x, and then transformations occur to that. Your absolute value function, y equals the absolute value of x. A basic quadratic, y equals x squared. A basic square root, square root of x. A basic cubic function. Excuse me. Thank you. And then a cubed root function. So, you, like I said, you know more than these. You did rational functions last year, which would look like this. So that's 1 over x. What else do you do? Do you remember any other functions that you did last year? Parent graphs? How about sine, cosine graphs? Remember those? You shift and stretch and do all that good stuff with those. We'll have a more in-depth chapter on trig this year. Doing some stuff with trig that just kind of over the years has been eliminated from Algebra 2. What else? Exponential parent graphs, so kind of this graph, which is some base to the x power. Yes, you did that. Log parent graphs, which is the inverse of exponential, so it kind of does this. Yes? I think that might be it. Radicals, rationals. Maybe not. We'll see if any more come up. But in general, those are the parent graphs you should be familiar with, the visual of those, because then we're going to transform them all. Now, the way I teach transformations, I like to have two columns, a vertical column and a horizontal column. All things vertical happen outside the function. So f of x in all of these cases is untouched. You might add or subtract something after the fact, you might negate it, or you might use some sort of multiplier. Now, in general, whether it's horizontal or vertical, adding and subtracting is indicative of a shift. Translation, same thing. When you negate something, that's indicative of a what? Reflection, good. And when you use a multiplier or a coefficient of any sort, that's indicative of a dilation. And with all of these, we would get more specific. Are we shifting up, down, left, right? Are we reflecting over the x-axis, over the y-axis? Are we dilating a stretch or compression? So we'll look at that. Obviously, I mentioned how all things vertically transformed happen outside the function, whereas all things horizontal happen within the function. So you can see the difference there. And then the other big piece is that your instinct as far as direction on vertical, all things vertical, seems to be logical. So like plus 3 means shifting up 3. You would think adding 3 vertically would move it up. Whereas all things horizontal is kind of the opposite of what your common sense would tell you. Most people would think plus 3, if you're thinking about horizontally, that's going to move you 3 units to the right. But knowing that everything horizontal is backwards, this actually means shift left 3. Subtracting 6 after the function shifts down 6. And subtracting 6 within the function means shift right 6. This is all a big review, yes? Kendall, what does this negative do? Reflect over what? Reflect over x-axis, correct. When you flip vertically, like from here and flip down, that's a reflection over the x-axis. So this one here is a reflection over a y-axis. And then what is this 1/2 f of x do, Liam? What do you mean get closer? The y coordinates, right. Not necessarily down, but they pinch in towards the x-axis. So I'm just going to use this and pretend that's my y-axis, x-axis. So anything that's above kind of compresses downward. Anything that's below really compresses upwards. They pinch in towards the x-axis. So we would say this is a vertical compression by 1/2. And the 3 is a vertical stretch by a factor of 3. Now, I think, Liam, you mentioned the y, right? Did you say that? Yes. Yeah. All things vertical affect the y coordinate because you're moving things up and down. Whether they're stretching up and down, shifting up and down, reflecting up and down, the only coordinate that's affected is the y coordinate. And on horizontal transformations, the only thing affected are the x coordinates as you move left and right. What does the f of 1/2 of an x do, Alyssa? I would say a stretch by 2, though, right? You're kind of doubling out all those x coordinates. So you take the reciprocal of whatever that coefficient is. So it's a horizontal stretch by 2. And Zach, what's the last one? 1/3, good, yep. So you reciprocate that to get the magnitude of your stretch or compression. Right, if it's a stretch, it should be greater than 1 when you describe it. If it's a compression, it should be less than 1. Total review, yes? Same for you? Okay. Describe the transformations happening, so this is all old news. Let's talk about the order. Okay? What kind of logic, Taylor, we'll use you, do you think through in order to decide what transformation would happen first? Oh, you lost your voice. Oh, then we're going to call on Maria. You work from the inside out. So inside, obviously, this one makes sense. So Winter, what does that do? Shift right 1 unit. Excellent. Okay, then if you're moving towards the outside, Maria, I'm going to go back to you because now you've got a couple options on the outside. Which one are you going to address first and why? This negative? Why? Can someone help her explain why we do? Actually, doesn't have to be the reflection next. You do have an option on the next couple of moves. What else could you do next, Adam? Right. These are sort of interchangeable. There are two different transformations there, but let's try to explain why either one of these prior to the +3. Go ahead, Adam. You kind of follow, you do follow PEMDAS. He's exactly right. You would have to, whatever x value you're plugging in, you would kind of address this first, then you would multiply by the coefficient, and then you would add 3 because you're following PEMDAS. And multiplication comes before addition. So, but the order of whether you address, the coefficient is -1/2. So whether you address the negative first or the 1/2 first, these two steps are interchangeable. We'll go with the reflection because that's what Maria said. Reflect over x-axis, vertically compress by 1/2, and then shift up 3. See, handout on graphing. Must have had a handout at one point in time. I no longer have a handout. I think I've since written it on the back. Is this exactly what we just did, right? -1/2 f of x minus 1 plus 3. I took the exact same function and I gave you just a generic picture of this, so that we are going to take this picture and do those things in the order that we just specified, okay? Definitely have a pencil handy, because if we actually go through 1 transformation, 2 transformations, 3 transformations, 4 transformations on top of the original graph, you're going to have 5 graphs all intertwined, which is going to be very confusing. My suggestion is draw your first one, and then when you go to your next one, erase the previous one so that you don't have them all sitting on top of each other. Or, let's think about this. Could we just take it point by point and figure out after each of these transformations what happens to each point? That might save some chaos in your picture. So let's do it that way. -1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So -8, 4 is an original point. After we shift that right 1 unit, what are the new coordinates going to be, Nathan M? -7, 4. There's that moving horizontally, affecting only the x coordinate. We said the negation first. After our reflection over the x-axis, what is that point going to become, Nathan Z? -7, -4. Very good. It's vertical, so it's affecting only our y-coordinate on that move. What's going to happen once we apply the vertical compression by 1/2? Kyle? Very good. Again, vertical only affects the y-coordinate. And then what's going to happen when we shift this up 3, Ellie? Nice. So we can kind of show, there's our shift right. There's our vertical reflect. There's our vertical compression. And lastly is our shift up 3. So that's where that first point, -8, 4, is now going to be at -7, 1. everyone on your own, go through all of that with this next critical point, negative 4, 4. And we can go through it with the rest of the critical points. Negative 4, 4 is a critical point. Negative 2, 0 is a critical point. Your y-intercept, negative 0, negative 4 is a critical point. 4, 0, another x-intercept is a critical point. And lastly, your endpoint, 8, 6. So take a few minutes to go through and figure out what each of those points morphs into. On your own. Go ahead, Connor. Okay, we'll list the final points for each of those. Okay, Lily W., what do you think happened in negative 4, 4? Negative 3, 1, did anyone get anything different? Good. That's what I got. Liz, what did you get for negative 2, 0? What did that become? Negative 1, 3. Did anybody get anything different? Good. 0, negative 4, Jack, where'd that go? 1, 5, excellent. 4, 0. Lily J., where'd that go? 5, 3, did anyone get anything different? And 8, 6, where did that go, Josh? 9, 0. So, good. So I don't know about you guys, but after a while I just found like it was more efficient. I did the second one the same way, but I just felt like it was more efficient to just take each point and just visually move them all in my head. So to not process all the points in between, I just kind of moved it and then just took each one through the 4 transformations and figured out where it ended up. Okie doke? Easy enough? Ends in 1. And the reason there's so few is because there are a decent number of sketches. Okay?
Yeah.
So whatever you find is the most efficient way of doing that. I kind of think it's taking point by point and just going visually through and then ending up and just writing your endpoints down. And that way you only graph the final product.